In this lesson, you will use z-scores and the normal distribution table to find areas or proportions under the normal curve. So remember our what if from the lesson on empirical rule? In that lesson, one of the examples was, suppose the heights of adult men are normally distributed with a mean of 70 and a standard deviation of 3. What if I asked you, what proportion of the men are taller than 75 inches? Remember in the previous lesson, 75 was not one of those special numbers that allowed us to use the empirical rule. Well, we will deal with this issue in this lesson instead. Recall, a z-score, or a standardized value, is the number of standard deviations a data point is away from the mean. A negative z-score indicates the point is below the mean. A positive z-score indicates that the point is above the mean. The formula for z-score is z equals x minus the mean over the standard deviation. We will use this a lot in this lesson. How does this correspond to our new normal curve? Remember that we can say something is normally distributed with the mean and standard deviation with this notation: capital N, parentheses, mu, comma, sigma. What we want to do is take any normal curve, regardless of its mu and sigma, and transform it into the standard normal curve. The standard normal curve is also known as the z-curve, and it has a mean of 0 and a standard deviation of 1. The way we do that is we find the z-score for every value in our distribution. You don't actually have to calculate that. You really only need to calculate it for what you're interested in. Standardizing takes this normal curve of men's heights and transforms it into the standard normal curve. If I can do that with any normal curve, then I can use my standard normal curve to find proportions or compare distributions using the tables that I'll show you a little bit later. Standardizing the normal curve makes them all the same. For example, if I have a gentleman who is 75 inches, on this curve, he's located right here at 75 inches. But over on this curve, where is he located? So what I want to do is take the z-score for 75 because I want to find out where the z-score is over on the other curve. Using the formula z equals x minus the mean over the standard deviation, I'll substitute in 75 minus 70 over 3 to get the z-score of approximately 1.67. So a gentleman who's 75 inches tall has a z-score of 1.67. The adult male that's 75 inches tall is 1.67 standard deviations above the mean height of all adult men. Why is this important? If I wanted to know the area above 75, which is my question, what proportion of the men are above 75 inches, I claim instead we can find the area above 1.67 standard deviation because the area is the same as the area over here. Why does that matter? Well, we have a table to find all of these areas for standard normal curves that we'll use extensively in this lesson. I'd like to introduce the standard normal chart. I know it's hard to read looking at it here, so it's been provided for you below this video player. I suggest printing this out if you can so you can use it throughout the lesson. Remember, our example had a z of 1.67. So now I need to find 1.67 on my normal distribution table. The way it works is this. On the left column, I look for the 1.6. I'm looking for up to the 10th place of my z-score. That is right here on the chart. Now the 7 is in the hundredths place. That's what I look for on the top of my chart. So I'll look for 0.07 on the top. So looking at 1.6 and 7, what I want to do is move over and down to get my area, which is 0.9525. That'll be the area we'll need. Going back to our picture, I found in my chart that a z of 1.67 gives us a proportion of 0.9525. What the table tells me is the area underneath that z-score. So the area under the z-curve for a z of 1.67 is 0.9525. However, what area is this on my picture? Is that the blue area that's shaded right here? Doesn't look like 95% of the curve is shaded. That's because it's not. Whenever you look something up on the table, it always gives you the value from your value down. Sometimes that's exactly what you want. Sometimes you want the other part of the curve. In this case, I don't want 0.9525. I want the other part of the curve. You know what that is because the area underneath the entire curve is 1. So if I want the blue area, I want 1 minus 0.9525, which is 0.0475. One of the things I suggest on all normal curve problems is to draw the picture. Draw the picture and do the shading. Here's why. Many times students will use the table to look up their answer and they get 0.9525 and they think that's my answer. But if I look back at my picture that we drew, I see the area right there is way too small to be 0.9525. Hopefully that triggers something that makes you think, is that really the area I want, or do I want to subtract it from 1? In this case, you want to subtract it from 1. Let's try another problem. In example 2, the heights of young women are normally distributed with a mean of 64 inches and a standard deviation of 3 inches. Based on the information provided, complete the following. A. Find the proportion of women who are shorter than 60 inches. B. Find the proportion of women who are taller than 66 inches. And C. Find the proportion of women who are between 60 and 66 inches tall. I'll give you a little bit of advice for this question. Follow these steps. Step 1. Draw the picture and shade. Step 2. Find the z-score. Step 3. Look it up on the z-table. And step 4. Decide what your answer is. Follow these steps for parts A through C. Pause the video to try this on your own. Click play when you're ready to resume. Here's example 2's solution. Part A. What proportion of women are shorter than 60 inches? I'll draw my picture. I'll find 60 and shade below 60. That was step 1, draw my picture and shade. Step 2, let's find my z-score. Write out your z formula every time. Substitute the numbers that you know and find your z-score. In this case, it's negative 1.33. Now I need to look it up on my table. If you're looking at the table in front of you, there are actually 2 pages of the table. One has positive z-scores and one has negative z-scores. Since our z-score is negative, we want to look at the negative page of the table. From our chart, the proportion for z less than negative 1.33 is 0.0918. Now, don't let this notation scare you. I want you to become familiar with it. When you look up a value on the chart, remember what it's telling you, which is the area underneath that particular z-score. What I'm saying here is that P, the proportion of values such that z is less than whatever your z is equal to whatever you find in your chart. I'll continually write that so that you can get used to that notation. The last step is decide on the answer. Is 0.0918 what I want? Or will I have to subtract it from 1 to get my answer? Looking at my picture, this is exactly what I want. The proportion of women who are shorter than 60 inches is about 0.0918. For part B, I'll go through the same steps. Find the proportion of women who are taller than 66 inches. Find 66 inches, draw the line, shade above it. That's the area that I'm interested in finding. Z equals x minus the mean over the standard deviation. Substitute the numbers that you know to find the z-score, which in this case is about 0.67. Go to your table, look up 0.6 on the left and 0.07 on the top. Go over and down, and what you'll find is the proportion of values such that z is less than 0.67 is 0.7486. Now, is this what I want? No, I don't want the area that is 74.86, which is the unshaded region over here. I want this shaded region, which is the small portion above 66. So I need to subtract this from 1 to get 0.2514. Therefore, the proportion of women who are taller than 66 inches is 0.2514. Lastly, for C, I want the proportion of women between 60 and 66 inches tall. I want the area in the middle. Our table does not give us the area in the middle. Our table only gives us from a point down. But we can use that information to find the answer. From part B, I know that the area of the tail over here is 0.2514. From part A, I know the area of the tail over here is 0.0918. Well, if I know this, but I want what's in the middle, I just take these two numbers and subtract them from the total area, which is 1. The proportion of values such that x is between 60 and 66 is 1 minus 0.2514 minus 0.0918, which gives me roughly 0.6568. Therefore, the proportion of women who are between 60 and 66 inches tall is about 0.6568. For those of you who've taken calculus, what you're really doing here is finding an integral. We're finding the area underneath a curve. Now, I'm not giving you the f of x function that describes this normal curve. I would need to do that in order to find the integral. The reason why we don't need calculus knowledge is because we have these tables. These tables tell us the area under this curve wherever we want. However, those of you who do have a calculus background, you can connect this with those integrals that you learned about. Now let's test what you learned so far with a check for understanding. Suppose the verbal portion of the SAT follows an approximately normal distribution with a mean of 505 and a standard deviation of 110. Based on the information provided, answer the following questions. A. What percent of students score above 600? B. What percent of students score between 450 and 600? And C. A student who receives a 650 on the verbal portion of the SAT is in what percentile? Pause the video to work on this. Don't forget to draw your pictures and shade. Click play when you're ready to continue. Here's a check for understanding solution. Part A asks what percent of students score above 600. On my curve, I'll label 600 and shade above it, and that's the area that I need. I'll find my z-score for 600, which is approximately 0.86. Go to your chart, look up 0.8 on the side and 0.06 on the top. Move over and down to find the proportion is 0.8051. Is that the area we want? No. We want 1 minus 0.8051, which gives us about 19.49%. Thus, 19.49% of students score above 600 on the verbal SAT. Part B asks what percent of students score between 450 and 600. Let's draw that picture. I'll label my 450 and my 600 and shade the area that I want. I do know this upper tail from part A of my question is 0.1949, but I don't know the bottom tail yet. Let's figure that out using z-scores. I'll find the z-score for 450, which gives me a z-score of about negative 0.50. Looking that up on the chart gives me a proportion of 0.3085. I don't need to subtract it from 1 because that's the area of the unshaded region on the left. However, what I'm looking for is the shaded area in the middle. I need to take these two tails and subtract it from 1. What I'm looking for is the proportion of people who scored between 450 and 600. That's 1 minus the 0.1949 minus the 0.3085. I can also write it as a proportion of z-scores that are between negative 0.5 and 0.86. Note that those areas are exactly the same. One of them is just talking about the curve that's describing the SAT scores, and the other one is talking about the standard normal curve. In either case, the answer is about 49.66% of the students score between 450 and 600 on the verbal portion of the SAT. Lastly, Part C asks, a student who receives a 650 on the SAT is in what percentile? Remember that percentile means what area is at or below the value you're interested in. So I'm looking at 650 and I want to know the area that is below 650. I can do this by finding the z-score. The z-score for 650 is roughly 1.32. Looking that up in my chart, I look up 1.3 and 0.02 on the top, and I go over and down to get a proportion of 0.9066. Now, is this the area I want? Yes, it is, because I want the area from 650 and below, which is about 90% of my curve. A student who scores 650 on the verbal portion of the SAT is at the 90.66th percentile. Now it's time for the wrap-up. After this lesson, you should be able to find the z-score for any normal distribution situation, use the normal distribution chart on the formula sheet to find areas or proportions under a normal curve, and use a normal distribution sketch to decide on the correct proportion. Is it exactly what the table gives you? Or will you have to do something like subtract from 1 to get your final answer? That concludes our lesson on z-scores revisited. Remember, you can review this video as many times as needed for better understanding. Thanks for watching.